So welcome back. In this part, this part of lecture 30, we're going to prove the Reisz Representation Theorem. So it's this remarkable theorem that says that if you're looking at a linear map from V to F in an inner product space, that linear map is actually the same as taking the inner product of V with some fixed element U. So every linear functional can be attached to an inner product with some particular U. So how do we go about proving this? Well, what we do is we let E1 through En be an orthonormal basis of V. Okay, and so we know that this exists by the Graham-Schmidt. We actually proved that in a previous lecture. So we know that V has to have an orthonormal basis, and because of that, we know that any element V can be written as V with the inner product of E1 times E1. V with the inner product of E2 times E2 all the way up to V times En, or the inner product of V and En times En. So this is for all vectors V and V. So when I apply my linear functional to any element V, it's the same thing as applying it to this big long expression, right? So this is expressing V in terms of this orthonormal basis, right? So we've written the V in terms of the basis. Okay, so that's just from above. And now we have that this is a linear map, right? So we could, and all of these inner product values are constant, so we can pull them out, right? So we have V1 comma E1 with phi evaluated at E1 all the way up to the inner product of V and En times phi evaluated at En. So this is the fact that phi is linear. Okay, and now what else can we do? Well, notice that this here is a number. All of these guys here are numbers, right? So these are actually constants as well. And so we can pull it into the inner product. We can either pull it into the first term or we can pull it into the second term. And what we're going to do is we're going to pull it into the second term. But when we pull it into the second term, remember that the properties of inner products tells me that I have to take the conjugate, the complex conjugate of that number. Right, so this is properties of inner product. Properties of inner products, because this is now this is an inner product and this is a constant. So we can pull it into either slot, but we have to take conjugate if we're going to pull it into the second slot. Okay, and now we can recombine again by the properties of inner products, that this is the same thing as V, comma, the inner product of phi, oops, let me clean this up here for you, the complex conjugate of phi evaluated E1 times the basis element E1 all the way up to En. Okay, and so again, this is properties of inner products. Okay, and so notice that what we have here is that phi evaluated at V is the same thing as the inner product of V with this particular element here. And on the right hand side, there's nothing corresponding to V. It's all in terms of your basis that you found. So what we do is we set U equaling to the element that showed up in the right in the second slot. And so what we have is that for any vector V, our linear functional is the same thing as taking the inner product of V with U. Right? So this is true for all V in V. So the first thing here what we have is that our linear functional can be expressed as an inner product with some particular element U. Now the next thing that we want to prove is that this U is unique. Right? So how do we usually show uniqueness? Well, we show that if there were two different things, right, a U1 and a U2, that they actually have to be the same thing. Right? So that's what I've done. I've started here. Suppose that our linear functional can be written as the inner product of V and U1, and it can also be written as V and the inner product of U2. So we can take this, because these two guys are equal, we know that 0 is equal to the first inner product minus the second inner product, right? And then this is the same thing using properties of inner product as V and inner product of U1 and U1 minus U2. And this is true for all V in V. So this is true for all vectors. So in particular, so now we're going to apply this fact to the vector U1 minus U2. What we have is 0 is equal to U1 minus U2 with the inner product of U1 minus U2. And we know that this can only happen if U1 minus U2 is 0, which is the same thing as saying that U1 is equal to U2. So this completes the proof because there's only going to be one U for which it works. Okay. So that's the Reisz Representation Theorem. Okay, so first of all, it's kind of nice saying that, hey, any linear map from V to F can be represented as inner product with a fixed U. And what I think is very nice about this result is that, let's go back to it. It says there exists a unique. Now, it's a uniqueness result. You know, sometimes these proofs show that such a thing exists, but it tells you you have no idea about how to find this element. But what I like about this proof is that the proof actually gives you a procedure to find this U. Okay, and what is the procedure? All right, you get a little algorithm. Well, first thing that you need to do is find an orthonormal basis E1 through En for V. And this we can do via the Gram-Schmidt process, right? So that's kind of what we learned in the previous lecture. Okay, so now you go off and you find your basis. Then what you need to do is you need to compute the complex conjugate of each of these values. So you have your basis, you stick it into the linear functional, and you take the complex conjugate. And once you've done that, you can actually return what the U is. The U is this constant times the basis element, E1, plus this constant times the basis element, and so on. So you can actually get your hands on the U from the theorem. And this is actually all embedded inside of the proof. So we're going to pause here, and when we come back, I'll give you an example of this procedure. And we'll also see an example of kind of applying the Gram-Schmidt. Okay, and I'm going to use kind of a non-standard vector space just to kind of make it a little bit more interesting about what we're doing.